Hi. Now please confirm if everyone can hear me. Okay, that's cool. Thank you for the introduction. Very sorry everyone for this delay. Okay, so this is Ashutosh and we'll be starting with the talk shortly, which is the introduction to Python as well as an introduction to astronomy. So I have joined with my computer also, so just let me know if you can see my screen now. Someone please confirm. Okay. Right. I have shared my entire screen. I can see it being shared. Right. Okay. So, yeah, that is because I have just opened that screen on my computer. Now, can you see the? Okay. Yeah. Okay, fine. So, everyone will just quickly start. By the way, Suji, I figured out the recording thing. The meeting is being recorded, so we can share the recording with the participants later on. Okay? Okay, fine. So, today's talk is on the applications of Python in astronomy. It'll be an interactive introduction. I requested people to just install Jupyter Notebook in their computers. If you have installed, I would like all of you to open that, right? So you can type on the codes simultaneously. Otherwise, we'll share the Jupyter Notebook later on. So this talk is from 1.4 Astronomy Club. We do astronomy outreaches. More is already spoken by Sujay. So let us already start with the subject, which is application of Python in astronomy. So to begin with, I have divided my talk into two parts. One will be an introduction to Python, where we'll discuss Python from the 0th level, assuming if someone has no prior knowledge of Python, he or she can also attend the talk. Secondly, we'll be talking about astronomy. We just will take one simple problem coming from spherical astronomy and try to solve that. So first of all, the first and foremost, why Python? Why do we learn Python? Why do we use Python in astronomy and astrophysics? Simply because Python is easy to learn. It has lots and lots and lots of extensive libraries. Often you find that the problem you're working on has already been solved by someone and it's available in the internet in the form of a library. We'll talk about what a library is. And again, strong community support, the same thing. Right. Sorry. Python and astronomy. So Python is, everyone would agree that it's by far the most importantly used tool in astronomy and astrophysics. Okay, it is used to analyze data, whatever data you take from telescopes, observatories, spectrographs. All of those need analysis. Those analyses have to be done by some programming language, and that language, the easiest one of them, turns out to be Python. It can be used to model, to simulate, right? It can also be used for machine learning applications for various models, right? We won't talk much about it. We'll just jump to our Jupyter notebook. This notebook will be shared later on. If you want to try coding right now, you can. Just a second. So you can actually run Python in various forms. One of them, the most interactive one, the easiest one, is Jupyter Notebook. You can download it or use it on a browser. It comes like with the Anaconda package. There are other compilers of Python, one being simply the IDE that comes with the Python installation itself. You can also use Spider, PyCharm, and other things. Just a sec, it's taking a bit long. Right. So I hope all of you can see the Jupyter notebook in front of on your screens. Okay. Right. So, okay, a very basic introduction to this Jupyter notebook. This is the interface that you see, right? Even if you just Google Jupyter notebook, you can use this notebook online. But some of the today's code won't work if you use online notebooks. Then, thing you see right here, you can see my cursor as well. Right. So, this thing over here is called a cell. Whatever you code is typed in a cell. Okay. You can change the form of a cell. There are various options out there. I won't waste much time talking about them. One thing I want you to know is whenever you type a code here, you have to run it using this command over here. There's a run command. Okay. Otherwise, you can just okay. Okay. Where was I? Yeah. Once you type a code in this cell, you have to run it. To run it, there is simply a run command over here. Otherwise, you can just press Shift and Enter together. Shift plus Enter on your keyboard, and the code will run. The good thing about Python is most of you must have learned C if you are in DU. Some of the students are from there. So there you have to write the complete code at once, right? You have to begin defining a function and do everything in just one complete file. In Python, it's not necessary. You can type literally lines. So I just have typed a very simple line in the first cell, which is where the traditional way to start learning programming. We'll just use the print command. Print command, as it speaks for itself, it just prints whatever text you give to it. Okay, so for example, I give it here hello world, and I press Shift and Enter, and there you go. It gets compiled, and on your screen, it prints the exact same message which was inside the print command. The message is given within double inverted quotes, and everything in between those double inverted quotes will be printed. You can also give single inverted quotes in Python. Right, you can just give single inverted quotes and it will just work the same. There is no restriction. Okay, in DU we learn Python only. I saw a message. Very time we used to learn C. Okay, so this is the very basic command. I hope it's clear. If there is a doubt, it's always welcomed on chat. Okay, let's go to our second subheading, which is expressions and assignments. Now, this is a very beautiful thing about Python. You can literally use this cell as a calculator, right? You can type a command as if you are using a calculator. I just typed some random expression. I don't know what was in my mind. It's just, I typed it and I pressed Shift and Enter. It will solve it. It's literally a calculator. It's a very handy calculator. Okay? You can work with fractions, you can work with integers, you can work with, I don't know, whatever kind of data you have. And with special caution, you can even work with very large numbers, which can't be done in other conventional programming languages. Okay. Second thing here is using variables. So whenever we do Python, we won't obviously use it as a calculator, right? We have calculators in market for that. What we use Python is for more complex programming problems, and therefore we sometimes need to assign variable names, just exactly the same as we do in mathematics or in other programming. The beauty again here is you don't need to define data type while defining variables in Python. For example, in Java or in C, you write int a equal to 5. or you write double or float c equal to 4.5e2. In Python, it's nothing. You just type the name, you just type the value. A equal to 5. I shouldn't read it as a equal to 5. It is literally a set to 5 because you can modify a later. In the next line, I can write a equal to 7 and it's completely legal. So yeah, this is how you define Python, define variables in Python, and then you can do math with variables. Just type the same expression, right? I just have typed a plus b slash c, which will divide b by c and add a to it. I press shift enter, and here is your result. By the way, I did not need to print this result, right? I did not need to use the print command. I could have, but I did not need. So this is a special feature this Jupyter notebook comes with, that the last line of your code snippet, if it has some outcome, if it has some output, it will be displayed just below the cell itself. I can obviously use the print command. I'll just write print a plus b slash c, press shift enter, and again here's a result. Oh, I had done it here, sorry. Fine. You can also give the result to another variable. For example, I define a variable res for the same expression, and now I can write my result in a more pretty looking manner. So I write print command, I write some statement which I want to present before my result, and then there is this formatting command in Python. Very sorry. So what I'm trying to do here is, so I press shift enter. Okay, so this print command, print a plus b slash c, prints the result of the expression I typed. Okay. This print command over here, this types some text and then prints some result, and that result is kind of cropped. So that is what this percentage sign over here does. This is syntax in Python. You may learn it. So whatever you write after percentage sign is how many decimal digits you want in your answer. For example, I wanted 5 decimal digits. I would just write 0.5, and f means that it's a floating point integer, that is, it's a real number. So if I write 0.5, now my result will be displayed up to 5 decimal digits. So this is the way to format strings to format outputs in Python. This is extremely similar to one in C. Right. Okay. Another line, a passing comment, that equal to is not equal to in programming. It is set to. So I set a to 5. Later on, I am totally allowed to modify it. I set a to 5, then I can even set a to a plus 10. This is a statement not allowed in Java, or not allowed in mathematics, but it's always allowed in programming. Okay. So a is set to a plus 10 now. That is what a was 5. Now it is set to 5 plus 10. Then again I can press shift enter to print a, and the result is 50. I saw a chart. Sorry to interrupt. What was that? Okay. Fine. Then we have control sequences in Python. What are control sequences? Control sequences are just loops. So you can loop in Python. Right? You can easily loop in Python as you can loop in other programming languages. For example, let us sum the first 100 numbers. Okay. First 100 natural numbers, we just do it very simple. We define a variable called sum. We tell the computer how many terms we want to sum, that is 100 terms, and then right. Now this is the for loop in Python. It is very important for today's talk. We will be using it left, right and center. So look at the syntax very properly. For I in range 1, n plus 1. What does the command range 1, n plus 1 do? The command range of 1, n plus 1 makes a range from 1 to n. This is very important. 1 is included, n plus 1 is excluded. That is why n plus 1. Okay. So if I want to make a range of 1 to 101, we have to 1 to 100, we have to type range 1 comma 101. 1 will be included, 101 will be excluded. So it will be a range from 1 to 100. And that's it, simple. Then you indent. Now this is pretty interesting. So this makes Python a pretty looking language, but you have to indent instead of using curly braces, which you might have seen, might not have seen in some programming languages. The blocks are defined using curly braces. Here they are defined using indentation. Indent means space. So usually you put a tab. You can put 2 tabs. You are completely free to do that. Okay. So I just put a tab here, and that means that whatever is indented, that is whatever is before whatever line I press a tab, will be a part of this control sequence and will be printed. So yeah, it's a familiar result. The sum of natural numbers from 1 to 100, it's 5050. And look at the speed of Python, right? You can do it up to 1000 terms. You can do up to 10,000 terms, 1 lakh terms, I don't know, whatever. This was for loop. There are other loops in Python as well. The one which might be familiar is the while loop. While loop, it's the basic syntax is exactly what while means in English. While I is less than equal to n. So the loop will keep running until I reaches n, and then inside a while loop I just modify my I. So I just modify my I as I equal to I plus 1. Again, look at the indentation here, and the concept is similar. I want to do the sum, so sum equal to sum plus number, and then I just increase the number by 1. This is very similar to for loop, it's just another statement. And run it, it again gives the sum. You can again do it up to x arbitrary number of digits, okay? Right, so these 2 loops we'll be using for today's talk. We'll be only going with the for loop. I don't think I have written while loop after this statement anywhere. If anyone has any questions till now, please do ask. Fine. Okay, so now we go to a bit technical part. All that was easy stuff. Now comes a bit interesting stuff. Modules and objects. So that is what I mentioned in the very first slide, that in Python there is a huge community support. There are a lot of pre-written programs which you can import in your program to make your calculations faster. Okay, so there is something called as a Python standard library. This is the link, which is, you can just Google it, Python standard library, or use this link. It comes with many packages or libraries. Okay, and apart from Python standard library, which the Python gives, there are other developers who develop libraries for Python. Okay, for example, one library which we will extensively use is SciPy. Okay, SciPy, it's probably stands for Scientific Python. Okay, so a library is written in a modular structure. What do I mean by modular structure? A module can have modules inside it. So there is a big code, and inside it they can define another codes which you can import. Right. So there is a complete library called SciPy, which is a very big library. So I can import it in my program. I have no issues. So I just write a command, import SciPy. This command again is similar to other programming languages. So import SciPy will just import SciPy from your computer. Of course, SciPy needs to be in your computer for that, which you can easily download. All of this is open source. But SciPy is too big, and I don't want the whole of it. For example, for now, I want a sub-program of SciPy, which is scipy.constants. Scipy.constants, it's useful. It contains a list of all the constants you would want to use in your programming. So the command import scipy.constants searches in your computer, catches scipy.constants, brings it in your code. Okay. Now there is a command, this dir scipy.constant. So if any library, you don't know what is in there, you can just use this command dir scipy.constants, and it will print whatever constants are there in the library. For example, let me just okay, one thing, this hash over here, this hash stands for a comment. So this hash statement, for example, I've written all those things over here. This will not be sent to compiler for compilation, or I would say interpreter. This is basically interpreted Python. It's compiled line by line. Okay. So this won't be sent to the interpreter. It will only be here to help the user or programmer. Okay. So for example, I just comment out this line. I don't want my computer to read this. I just want to run the code till dir scipy.constants. I run it and see this black dot over here says that a program is running. Now it has gone white. Next time I compile, just look there. So there you go. These are all the constants available in the scipy.constants. Okay. So suppose I'm an astrophysics person. Suppose I want the value of G, Newton's gravitational constant. Just type G and there comes a number. It is 6.6743 E minus 1. E means exponent. E is here 10 to the power, not e to the power. Okay. Again, scipy.constants is a very big name, right? We can give a shorter name to it. So I can just import scipy.constants as const. What does this do? This just renames. How does this rename? It just, whenever you type const now, it stands for scipy.constants. The command is as simple as that. Again, the same thing, const.g. Here also I've written dir const. Why did it not get executed? Because it's not the last line. If I put a print command here, it will get executed. Let me just quickly demonstrate that. Alright, there you go. These are all the things available in the scipy.constant submodule. Now, you can even go beyond that. If you don't want to import scipy.constants completely, if you want your code to be more memory efficient, you can just type from scipy.constants, go to scipy.constants, and from there import G and C. I just want this gravitational constant, I just want speed of light in my code, and I don't want anything else, right? I just want to import two numbers from that program. It will do it. Python has no problem. And then if you write something like G comma C, it's very interesting. You don't need to go to different lines to print something. I can just print, I suppose I want to see G and C, I can just type G comma C. Python will print both of them. Right. So this is here G and C. Interestingly, Python has the exact value of C. One thing, this small thing over here, the output, two numbers inside a parenthesis, like in mathematics, this is given in tuple in Python. We won't really be using tuples today, but trust me, they can become very, very, very handy at times. Okay. Now, there is another library. One library was SciPy. There is another library called AstroPy. AstroPy is astronomy in Python. I don't know what the exact full form is. It contains various things we need for astronomy. Today we'll be extensively using AstroPy. You can again do the same thing. Type dir astroconst. It will print all the astro constants. Alright, I just have again imported astropy.constants. I can import complete astropy as well. I have no problem doing that. Okay. In fact, in the astronomy section, we'll be doing that. Okay, at times. Now, astronomy has constants which are related to astronomy, of course, and astrophysics. So, one constant which is there is mass of sun. So, Python has mass of sun stored in its program. You just import it. You want to see it, you just print. And yeah, it gets printed. Now, this in font as well as in appearance is a bit different than all the outputs you saw above. The reason is, one thing you can see is it has units. So this is pretty interesting that it's not just a number in other programming languages, what would you usually have? You will have a number 1.988 whatever into 10 to the 30, and that is it. It will not have units. The computer will have no information on what it means. But here the computer for sure knows that it's a unit, it's a mass, and its unit is kilograms. Very important thing in Python is everything in Python is an object and it has its attributes. Even these things over here, G, C, even if I type a 5 on my keyboard and print it in Python, it will be an object. Okay, what does an object mean? An object, it has various attributes. It has various characteristics to it. So for example, if I print astroconstant.m sun, you see it has so many attributes. It contains whole lot of information. It knows that its name is solar mass. It's known as solar mass in astronomy. Its value is something like this. It has uncertainty. Okay. Now look at this. It's pretty interesting whether the uncertainty is of the order of 10 to the 25, greater than the mass of Earth. Its unit is kilogram. You have the reference where this value was finalized. Okay, and when you update your AstroPy on your computer, this value will get updated as there's a change. So all of this was basic Python. So Python is a very handy, easy to learn language. You see, you literally need to learn nothing over here. If you have done even a little bit of programming before, Python would be super duper easy. Okay, right. Okay. Now we'll discuss a bit of astronomy. We'll see how Python helps us solve few problems, not few, a lot of problems in astronomy. We'll be doing astronomy here, no astrophysics. Okay. So to begin with, I don't know if you guys have had an astro course. So in astronomy, okay, first comes the concept of the coordinate system in astronomy. So whenever you study physics, the 11th grade physics, very first chapter in your book was motion in a plane, and the very first topic was reference frames, inertial frames, non-inertial frames, what are axes, what are unit vectors, all those things, right? So to study motion, you need to have a coordinate system with you, right? You need to specify, I want to observe something at that location. I want to observe something moving at that speed or whatever. So the most obvious system in astronomy was to use some spherically symmetric system, because when you look up at the sky, you essentially look at it like a star, right? So what you do is, this at the center is your Earth. You just make a arbitrarily big sphere, I would say congruent with Earth, that is having concentric with Earth. It has the same circle, same center as Earth has, and this sphere is arbitrarily big. I don't know how big is it. Make it as big as you can imagine. So it is like a sky. So at night you see the sky. It's essentially like a hemisphere because you can't see below the ground, but it's still like a sphere, right? And you see all the objects against that sphere. You see all the stars, you see all the planets, you see the moon, all projected on that sky, which is a hemisphere. I just borrow that concept and put it in astronomy. I define a big sphere which gets the name celestial sphere, and all the stars, planets, everything you have in sky is assumed to be projected on that very sphere. So one thing which I ran away from is the distance of objects from us. And frankly, it's not easy to find distances. And when we do astronomy, at least we just refrain from talking about distances. What we talk about is the location on the sky of an object. Okay? Right. Now, it is very similar to the coordinate system on Earth. So, for example, if you guys are in Mumbai, you have two coordinates, right? You have a latitude, you have a longitude. If you are in Delhi, your latitude and longitude are different, right? So, if I give you the latitude and longitude of a place, you you know exactly where the place is on Earth. There is no contradictions, right? So two coordinates, because it's a two-dimensional sphere, are sufficient to specify the location. Similarly, I just borrow exactly the same concept and define two coordinates called right ascension and declination on the celestial sphere. But I need to have some cardinal points, right? So I have Earth. Earth has a north pole. If you just project the Earth's rotation axis and see where it cuts the celestial sphere towards the northern side, you just call that as the north celestial pole. In simplest layman terms, north celestial pole is the point right overhead you if you are at the north pole. So it's a point on the celestial sphere exactly north. Okay, if you stand at the north pole, the point right above your head will be the north celestial pole. Similarly, you can have the south celestial pole. Okay, now you can have celestial equator. What is celestial equator? Celestial equator is basically Earth's equator projected on the celestial sphere. So you had a celestial sphere, you had Earth, which was at the same center as the celestial sphere. You make the equator big, and the equator essentially gets projected on the celestial sphere, and we call that as the celestial equator. So celestial equator is right above celestial, Earth's equator. What else? Right. Now you see that red curve over here, red circle over here. Now this red circle, it's pretty important in astronomy. This red circle, it is called the ecliptic. What is it? Ecliptic is the path on which the sun moves. So sun is a very important celestial body for us. We define our day and night because of sun. We experience seasons because of sun. We have life because of sun. So this motion of the sun on the celestial sphere is given a name. It is called ecliptic, and it's repeatable. It repeats. The sun, if today you look at the sun sometime and exactly 1 year at the same time, you look up, you see the sun at exactly the same spot. Okay. So now I have two circles. I have one ecliptic. I have a celestial equator. Of course, if I have two circles, they are projected on a sphere, they'll intersect at 2 points. One is here, one is here. There are 2 points at which these two circles intersect. These 2 points are called points of equinoxes. So you might have heard the term equinox before. Equinox, it has the same root as the word equal. Okay, we'll see what exactly these things mean in the next few slides, but for now I want you to just grab the names, take my word for it. Scientists named one as vernal equinox and one as autumnal equinox. Okay, so right, so I defined all the cardinal points. One thing, there is a fixed angle between these two circles, the ecliptic and the celestial equator. So right now they are inclined at an angle of 23.5 degrees, which precisely is 23.44 degrees. In old days, when astronomy was being developed back in Greece and in India, the obliquity they observed was 24 degrees. It changes. Basically, there is something called as nutation, I guess, due to the tidal forces. The Earth just nutates, it just nods. And that nod, it has a time scale, but over our observational scales, it's nothing. So we take it fixed, we take it 23.44 degrees for now. Okay, so now I look at the star and I project it on the celestial equator. I have a star, I project it on the celestial equator, and I measure two angles. One angle is the angle measured from the vernal equinox. Okay, that angle is called alpha or right ascension. Okay, and it is like a longitude. Okay, so for example, longitude, you have the vertical lines, right? So you have the vertical lines, 0 degrees somewhere in Greenwich. So right ascension is exactly similar to that. You just project your star on the celestial equator and see where it intersects it, and that angle measured from the equinox along the celestial equator is called right ascension. And then you have declination. Declination is how up it was, how much you had to come down to bring it on the celestial equator. It's exactly similar to latitude and longitude. Literally, no differences. Okay. I repeat, if this might be something new for most of you, so if you have to ask questions, it's completely fine. Okay, just ask your doubts. Okay, so there are conventions. Alpha is right ascension, delta is declination, and epsilon 0 or epsilon naught, if you like, is the obliquity of the ecliptic. So I defined three things on this slide, which is very, very important. I defined celestial sphere, I defined RA deck, and I defined epsilon. We'll be using this a lot in our codes. Okay. Now this celestial coordinate system, it's universal. It is not observer dependent. For example, if I'm in Bombay and you are in Delhi and someone is right now in, I don't know, is in USA or is in ISS, they'll all follow the same celestial sphere, the same celestial coordinate. The coordinates of every object, RA and deck, will be same for everyone anywhere around the world. Okay, it is exactly like latitude and longitude. If I ask you what is lat lon of Delhi, it is, I don't know, 2878. So how can we align with Earth's rotation? Okay, excellent question. So we haven't taken care of Earth's rotation right now. We just assume that Earth is stationary. I haven't defined any observer anywhere, local observer anywhere, sorry. I just have assumed that Earth is just a stationary point anywhere and there is a sphere surrounding it. And that is exactly where I was getting to, that Earth is rotating. And therefore, locally, sky is different from for everyone. I borrowed this concept of celestial sphere from the concept of sky. But sky is not the same. Sky for you right now might be different from for sky for me. Right? And therefore, I need a local coordinate system, a coordinate system which is local to every observer. Okay? So, I define something called as horizontal coordinate system. Oh, by the way, the very large part of today's talk I've borrowed from these Python notes or astronomy notes from these undergraduate lecture notes in physics. It's very beautiful, just have a read. Okay. Let me just. Sir, what if I am right? Yeah. So if you are on a space shuttle and I ask you where is Delhi, you still say 78 degrees east and 28 degrees north, right? You don't worry about where you are. Okay. So this coordinate is universal. If this is defined, it's defined that Earth is at the center, there is a sphere, it doesn't care about who is observing, from where is observing. It has a fixed origin, it has a fixed orientation. Okay, I hope that answers. It's a very important point. Good questions. Right. If I want to, now essentially, right, these are measured. Yeah. Yeah, exactly. So RA and deck, the origin for this coordinate system is essentially the center of the Earth. The angles are measured from center. Okay, so therefore it doesn't really matter where you are. Okay. Okay. I hope that answers. Now, essentially, when I make an observation, I am sitting somewhere, right? I am a local observer, right? I can't go to center of Earth and then see What is there? I am on the surface of Earth and I am in Rome. I may be in Mumbai today, I might go to Delhi, I might go to Singapore, right? And I want to observe things. So for that I define something called as the horizontal coordinate system or alt-as coordinate system. It has a different name also. Now this is very simple. This is extremely easy. So right here is the observer, that is you. The plane on which you are standing is this exact plane. This has nothing to do with Earth's equator. Okay, in the last slide, this plane was the Earth's equatorial plane projected outwards. This plane is just the plane you are standing on right now. So, for example, if you are really standing on the surface of the Earth, so you draw a tangent to where you are standing, and that exactly is this plane. And then there is horizon. Right, horizon is the limit to where you can see. Yes. And then the plane, it divides the sphere, the local sphere. It is not really, it is the celestial sphere, but I won't call it celestial sphere. Okay, it's just a local sphere that you can see. It divides it into two parts. One above the horizon, which you can see ideally if there are no buildings, mountains, pollutions, rain. I'm sorry again. Above the horizon, you will see that. Below the horizon, that is, you can't see. Okay. Here you define 4 cardinal points or 6 cardinal points. So one is the north point. Opposite to it will be the south point. Face north, your right hand will face to east. This is the east point, and somewhere here will be the west point. So the directions that you have studied from your geography class, north, south, east, west, these are the 4 cardinal points I need. And then I call something as the zenith. Zenith, it means the highest point, the point right above your head if you are standing on a horizontal graph. Okay. So these are the 5 cardinal points. There is a point right opposite to zenith, okay, which makes it 6. And then it's almost similar system to area and deck, lat and lon. You need 2 coordinates, 2 angles. This time you called in altitude and azimuth. Altitude and azimuth. That is why the name for this coordinate system, which is alt-as coordinate system. Okay. One thing to note here is there the azimuth. The right ascension was measured from vernal equinox, and here the azimuth is measured from the north. So you face north, you start measuring an angle eastwards, you measure azimuth, and altitude is exactly same as declination. It is just that this system now is local. One point which is important here is something called as the celestial meridian. So you have 3 points. You have the North Pole, you have the South Pole, you have the zenith. You make a circle connecting all these 3 points projected on the local sphere which you have, and that circle is called as the celestial meridian. Okay, so celestial meridian, remember, is north to south. Okay, so this is done, this is done. Right, I guess this should answer the doubts of how to take care of rotation of Earth. So this is how you take care of rotation of Earth. You define a local coordinate system. So you have a global coordinate system, which is same for everyone, and then you have a horizontal or a local coordinate system, which depends on where you are. Okay. Any doubts so far till here? Okay, cool. Now let us do a bit of math, right? So declination. So for a star, the location of stars are fixed in universe. They move very slowly over time scales of millions of years, right? We are not really worried about that. But for the planets which are in the solar system, when we observe them, their coordinates do change. And today we are concerned about a coordinate declination of the sun. Declination, remember, was in the celestial coordinate system. So for stars, dec will be fixed. If you Google or don't Google, we'll find it out in Python. If you type some command in Python and ask Python to give you declination for the star, for any star, you type the name, Python gives you the declination. It will be fixed. Do it after 5 years, it will be fixed. But if you do it for a planet or do it for sun, the declination will be different. The declination changes. And this is because the motion of the earth is exactly moving around the sun, right? And other planets are in close proximity of this motion. But the stars, for example, they are far, far away. For them, this really small motion of rotation of Earth around Sun, revolution, sorry, of Earth around Sun, it really doesn't matter, and their coordinates don't change. Okay. Now there is some scary psi equation on your screen. This is just an approximate formula. This is a very big and still an approximate formula to calculate the declination of the Sun. So you input in this formula today's date, and this formula outputs the declination of Sun for today. Here, so what are the terms? Delta is declination, epsilon 0 is obliquity of ecliptic, which is a fixed number, 23.44 degrees. N is the number of days starting from January 1st. January 1st is 0. Okay, so for today, I counted in the morning, I forgot, it's some 196th day, I guess. Okay. And then the small e, this factor we are going to ignore for today. This is actually eccentricity. Eccentricity, because the orbits, you might remember from your classical mechanics class that the orbits of in a two-body problem of a planet around the sun, they are not really circles, these are ellipses, right? And ellipse has an eccentricity. So the eccentricity of Earth's orbit is pretty low. I don't remember the value, it's pretty low, it's almost circular orbit, and that is why Sun does not become bigger and smaller through the course of the year. We are approximately at a uniform distance from the Sun. Okay, so yeah, this is epsilon, E, eccentricity, and then again, N is the number of days starting from January 1st. Right, now there are two things. One is solstice and one is an equinox. Just a sec. Need to plug in the laptop. Right. So there are two things which we need to remember. One is solstice and one is equinox. What is a solstice? There are two solstices in a year, two solstices in a year. Sorry for my spelling. So what is a solstice? Solstice is when sun's declination is maximum. That is either it is plus 23.5 degrees or it is minus 23.5 degrees. That is when sun is either here or when sun is either here. So these are right. So when sun is right either here or sun is either here, that is the maximum and minimum declinations of the sun. Then there is equinox. Equinox is when the sun's declination is 0. Okay. So the solstices, as you might remember from your geography classes, they come somewhere in the winter solstice, which is 22nd of December, and then there is a summer solstice, which is 22nd of June, it just passed. And then there are equinoxes, which are in March, 21st of March, I guess, and 23rd of September. Of course, the dates vary. These are not exact dates. And now you will know the meaning of this vernal equinox and autumnal equinox. Vernal equinox, see the sun's declination is 0 here. Vernal equinox is when the sun crosses the celestial equator and it is spring. They call it vernal equinox. And when it does in autumn, that is in September 22nd, we call it autumnal equinox. Day and night are of equal length, you must have heard on this day. Right. Okay. Let us play with Python a little till here, and then we'll get back to slides. Okay. So, alright, let's do a bit of astronomy. If you were coding with me in the first half of the lecture, it is cool, but in the next half, the codes are going to be a bit lengthy and a bit difficult to type real time. So, I would request to just have a look at them. Okay. So, we'll anyway share the Jupyter notebook and the video recording. Alright, now I introduce you to another library in Python, which is math. Math, as its name suggests, it does math. Okay, it has various sub programs to do various mathematical to perform various mathematical operations. Okay, so for example, if today's day, it is 196th day starting from January 1st as 0th day. Okay. I define a variable called day. I give it a value 196. I want to find today's declination for sun. And then you have omega. Omega is the angular speed of Earth. It is in radians per day. So see, I have a module math. Sorry for type. Oh, it was fine. Okay. Yeah, so I have a module math. It has a sub object pi. Pi is the familiar pi. It contains the value of pi. When you write math.pi, the value of pi gets into your program. Okay. You could as well have written from math import pi, or you could have just written import math.pi if that were the only thing you were using. Okay. Math is, by the way, you don't need to install it. Alag se, it comes in Python standard library. Okay. It comes as you install Python. Why did I divide it by 365.24? Because that's how long the year is in days. Then you have epsilon, the obliquity of the ecliptic, which is 23.44. So for Python right now, it is just a number. You gave it in degrees. You know that the standard units in which the programs work are in radians. So I convert epsilon to radians. I could have done it manually, multiply by pi over 180, but there is a built-in function in math to perform this conversion. Then I apply the same formula. I cheated a little bit here. The formula was a big one and I was lazy to type. We usually ignore this E factor over here because E is a really small number. Earth's orbit, take my word for it, is circular. Okay, so the results we get by just the first half of the formula is usually correct. So yeah, you just do all the things. Math.asine, asine is sine inverse, math.sine, math.cos, multiply, divide, whatever it is, and then print. Now this is another command to print. Okay, I would want you to look at the syntax over here. It speaks for itself. I want it up till 2 decimal digits. It's a floating point number. I just do dot format and in the parenthesis whatever there is. You can as well use the earlier format syntax which I show. It's just to introduce you to new things. Right, and it just prints the declination today is 21.47 degrees. Makes sense. Right, because just 15 plus 8, 22 days ago, it should be a solstice. The declination should be 23.44 degrees. And you can do that. 16 days ago would be 180 days, right? Yeah, approximately 180th day would be a solstice. And there you run, 23.24 degrees. Right, if you just search around, you will find the exact day. Right. So, in fact, I have something here. Oh, I should have written 170, okay. Right, so I just made a list of all the solstices and equinoxes. I counted them. They come at approximately these many days, 80, 170, 265, 355, okay. And the main motive of this exercise is to introduce you to something called as an array. An array is like a list of numbers with which you can do faster calculations, okay. So suppose you have tons of data and you want to do some calculations with it. you better not do it one by one. You define a data type containing all of the information at once and do the math with it, right? And for that, there is a package in Python which is called NumPy. It is numerical Python. It is seriously the most important package you will ever come across. You will almost in every program, if you write for science purpose, you will write import numpy as np. It has a standard nickname np. Okay, and the way to define an array is you just write np.array, and it's beautiful. If you do it in C or if you do it in Java, you just have to write double array equal to. You have to make square boxes, define their sizes, then make a loop, and then fill the array. Here it's simple, simple. You just have to write np.array, and in the bracket you can write the list which you want to convert into a array. Okay, and then you can access the array by just writing its name. Right. You can access elements of array. So Python is 0 indexed. 0 is the first element of the array. 1 is the second element of the array. 2 is the third element of the array. And 3 will be the last, but minus 1 is also the last element of array. So this is really cool. If you have an object which you can access from the end, you just have to write minus and the index of that object starting from end. So minus 1 will be the last, minus 2 will be second last, minus 3 will be third last. And the beauty, you can do nothing changes. So in other coding, you have to loop through an array to do the calculation. Here, you don't have to, you just have to input the array. See, I just inputted day array to this exact same formula, and it does the calculation for all the 4 numbers. And here it's just 4, but it can be billion. It can be equal to your computer's memory. Okay, you just put it in and press shift enter. Okay, I just have put delta here. I just need to put delta air because I stored the result in delta air here, right? So now I press shift enter, and there you go. These are the declinations on these respective days, and they make sense. 23.5, 23.5, 0 and 0 for equinoxes and solstices. Okay, simple. It's really fun. It's easy. And now we get to a bit more technical stuff. Before that, if anyone has any questions, please do ask. Let me just check the chart meanwhile. Right. Anyone? Any questions? Okay. Now, the diagrams keep on becoming more and more messy. So, diurnal arc. What exactly is diurnal arc? So, if you are sitting at a location on Earth and you observe a star, the star moves in an arc. It rises in the east and it sets in the west, and it follows an arc in between, right? And that arc is called diurnal arc. As simple as that. The sun follows an arc. All the planets follow an arc. Everything, it follows every object in this sky, even a space shuttle, as someone mentioned, it follows an arc. And that arc is called basically the diurnal arc. Okay, I already defined celestial meridian, right? Celestial meridian is the arc which joins North Pole, South Pole, and the zenith. Zenith is somewhere here. Now, there are two arcs. One is celestial meridian, which is north, south, and zenith को join करने वाला arc. One is the diurnal arc. That is the path every object is following. One is going north to south. One is going east to west. So obviously, both the arc will intersect at a point, at some point, and that point is the highest point of the object. Highest point in the sense that it is the highest altitude. Altitude azimuth, remember from the coordinate system, it is the distance above the horizon. So that is the highest an object will get through the course of the day. Okay, and diurnal arcs are generally, I'll say always parallel to celestial equator, exceptions being sun and planets, sun and moon, I would say, because these objects change their declination on a daily basis also. For a star, it will always be parallel to celestial equator. And it makes sense because the Earth is rotating and the celestial equator is perpendicular to the axis of rotation, right? If it's not obvious, leave it as a fact, okay? Then, so the red arc over here is the celestial, this diurnal arc, okay? Now there are two things I have mentioned, H rise and H set. So let us discuss what is H here. So H is something called as the R angle. R angle, it's connecting R and angle. It's connecting time with angle, time with astronomy. So what we do is, so on daily basis, the position of an object changes in the sky, right? So for example, sun at 8 a.m. is somewhere in east and sun at 6 p.m. is somewhere in west. So how do you characterize that? How do you just parameterize that? You just define a variable called as R angle. R angle, it should make sense. 24 hours is equal to 360 degrees, right? So it is to just give you a feel of what time where the object is, okay? The zero of this R angle is taken at the highest point. What is the highest point? The point where the two celestial equator, celestial meridian and the diurnal arc of an object intersect, okay? 24 degrees is 360 hours, 24 hours is 360 degrees, but please be a bit cautious because it is this hour over here is not same as one solar hour, it is slightly less than that. So this type of time is actually called as sidereal time. If you have heard the term before, so basically a sidereal day is 4 minutes shorter than mean solar day. So the reason being because in solar day you just have to account for the fact that Earth is also moving forward, right? If you look from the sun's frame of reference, Earth is moving almost 1 degree per day, right? 360 degrees in 365 days. So Earth is really moving forward and therefore you have to take care of that and therefore you have to add 4 minutes to that. And eventually because we always wanted sun to rise in the morning, we set all our clocks according to the mean solar day, which is 24 hours. The sidereal day is defined with respect to the stars. It is the time in which the star completes this 360 degree motion around the Earth, or in more simple and straight terms, it is the exact time for 360 degree rotation needed for Earth, okay? So it is that time and this R angle, it essentially represents that time, okay? The R angle, I would not have time to derive the formula, but the R angle at which the object sets, it has a formula, it is given by cosine of h set is equal to minus tangent of delta, tangent of phi. So what are delta and phi? Phi is the delta should be declination and phi is the latitude of the observatory where you are observing from, okay? And then if you have the time for h set, if you know what is the R angle when the object sets, because the path will be symmetric, right? The time what the object takes to go from here to here will obviously exactly be same as time it takes from here to here, and therefore you can find the diurnal length of an object in the sky, which will be 2 times this h set. One thing I bypassed here is if you apply this formula, you get h set in radians. So first you convert it into degrees and then you make this use of this thing that 24 hours, it corresponds to 360 degrees, okay? Right, it's time to go to Python. This was the last slide of science which we'll do. Now we'll solve a problem using Python. Let me know if you have any doubts, anyone? Okay, so cool. So we solved the problem of declination and now let us go to the the most beautiful part of today's talk. So, I'll tell you what the problem is. I will solve two problems. One is to find the length of a to find the daylight length at a location for a course of the year. So in winters, the daylight is for less time, right? The days are 10 hours, 11 hours in whole of India, right? And the in summers, the days are somewhere in 13 hours, 14 hours. So we'll solve what is exact day length for every day of the year. Okay? And how can we solve that? So it's simple. We'll start with very basic playing with the modules first. So AstroPy, I introduced you to AstroPy, right? So AstroPy has another subprogram called coordinates. It has coordinates, simple. It has not only coordinates of astronomical objects, it has coordinates of Earth also. Okay. So there I import two subprograms called SkyCoord and Earth Location. You can as well as have you could have written astropy.coordinates.skycoord or astropy.coordinates.earthlocation. Both are allowed formats in Python. And then there is a star called Vega. Okay, Vega is I guess right now it's one of the brightest stars that you can see if it's not raining at night. So we'll worry a lot about that today. So what I do is I ask the SkyCoord function that okay, I give you the name of the star Vega, search in your directory, whatever you are, search, I give you the name, I called SkyCoord from name. There are other ways which you can call the objects from SkyCoord. I'm using name. Name is Vega. I write the name, the SkyCoord gives me the coordinates of Vega. So I run shift enter. It's taking a bit of time for two reasons. One is my computer is slow. Second is the directories are pretty large. So yeah, it gives you right ascension and declination of Vega. And these are fixed. And someone asked if we are in a space shuttle, what are they? These are they. These are just two numbers. These are given for an object. If you go to moon, right ascension and declination with the celestial coordinate system, they don't change. They are given. Okay. So these are the right ascension and declination for Vega. Fine. Right. And I told you everything in a Python is an object. So you can call its attributes. I call Vega.dec, the declination of the object Vega. By the way, I named the object Vega itself. And I call the right ascension of the object Vega. I print both of them. And here they are. And it's cool. So AstroPy is really cool because see, it worries about units. It is 38 days, 38 degrees, 47 minutes, right? Yes. Oh, very sorry. Okay, thank you. Okay, right. So yeah, so those were strings, so it didn't really matter, but yeah, look at me. So right here you go. Okay, so everything is an object, you can call it, it has various attributes, it has units. Okay, now let us start to solve two of our problems. So suppose we want to study the dual arc of Vega from Redford, Delhi. That's the best place I could think of for today. We want the coordinates. Okay, right. Now I want to be a local observer. Celestial coordinates are universal. They don't worry about where you are, and therefore they don't give you local information as well. Now if you want a local coordinate system, a local horizontal coordinate system, you need to tell Python that where you are. And how do you tell Python? You give the Python the location of your observatory. So first of all, you need to give it in degree, minute, second. So you import astropy.units. It is a module which assigns units. Okay, it has a list of all the units. And if you want to give units, for example, I want it to be 28 degrees. So I multiply it by u.deg. U is a program in which there is another program deg, which stands for degrees. Okay. So this you can Google. This is the location of Redford, 28, 39, 22, 28 degree, 39 minute. 22 seconds, 77 degree, 14 minutes, 27.6 seconds. And this is given to an object called ops. It's a variable, it's an object. In Python, there is no longer a difference. And Earth location is the program. Earth location is the program in AstroPy package which gives the location to the object ops. Okay, and for for this particular problem, I just need the latitude. So remember that find the set ka formula. I need that, so I just take ops.lat. Lat I myself have defined. Okay, so you might want to ask why I really do that. Can't I just give phi ko seedha latitude? Why do I really need this earth location function? Yeah, I agree. You can directly give phi ko the latitude of this observatory 28, 39, 22. You just have to convert it into a number. Okay, you are allowed to. But once I give these units and all, it just becomes more standard. Now, if I want to later use some AstroPy package, then AstroPy package would require ki, what units have you given me data in? And therefore, I need to convert it into a good object, which is Earth location object. Fine, so I just run it, shift enter, and there it runs. So since there was an equality in the last line, nothing got printed. I can as well just write phi here, it will get printed here. So yeah, there is the phi. So see, this phi, it has units. It's not just a number, it literally has units, okay. Now, I just, okay, this is redundant. Once you import something, you need not import it again. You can just compute math by the formula I gave you, and you have to convert now this delta and phi to radians again, whatever units they were in. So I'll convert them into radian using the command .radian. You see, even delta and phi are objects in Python. They even have properties. They can be written like delta.radian. In other programming languages, this is not usually allowed. Yeah, so you just press shift enter. I guess Python did it. Now this h, as I told, you must have gotten it in radians right now. Right, because that is the standard unit of trigonometric angles. Now you want to convert it into hours. So now look at this. I have radians. I convert it into degrees first of all, and then I convert it into a sidereal day using the units module from AstroPy. Okay, so AstroPy has this units thing which has list of all units, and it has a unit called sidereal day, and you just convert it into sidereal day. Now a better unit would be hours. So AstroPy doesn't stop here. It has a unit. It has a function called to. If you write dot to u.h, it converts it into hours. So you just print the h set. And yeah, so I calculated t. I did a trick here. I should have multiplied by 2, right? Yeah, so I calculated h here. I multiplied h by 2. Why did I multiply h by 2? Let's go back to slides. I multiplied h by 2 because of this. So the h I calculated is basically h set. Okay. And 2 means because I want to find the diurnal length of an object in the sky. Okay. So that is 2 times the time taken by the object to go from its highest point, which might not be the zenith. Remember, it's just a point where it intersects the celestial meridian. It's just the time taken by an object to cover the entire path will be twice the time taken by object to go from highest point to setting point. Okay, right. Now this is cool. This we did. Right, now we can do this calculation for an entire year. Suppose I want to find what is the daylight time for all the days of the year. What do I do in Python? It's simple. You create a NumPy array. Now the trick I told you to create NumPy arrays was np.array and type the complete list in there, right? And to type numbers from 0 to 364 out there, because we start 0 as January 1st. It would have taken us ages. Yes. So there is a built-in command in Python called arange. What does arange do? np.arange. It just creates an array from 0 to 364 4. Remember, last element is always excluded. So 0 to 364, I could well have written np.array 0 to 364, 0 comma 364. If you want to create an array not starting from 0, you can always, if you want to create an array which does not start from 0, you can as well start the starting point. You can create an array from 10, 20, 10 to 19. Right, so I do exactly the same calculation. I calculate, I redefine omega for completeness. I define this epsilon, right, ecliptic, I should have written eps, right. So this is obliquity of ecliptic. Instead of just one delta, I will now get an array of deltas. And look how fast Python will do it. Just focus on black dot which will appear here. I'll press shift and enter. Done. On my screen, I couldn't even see the black dot. It's so fast. And it literally did it for 365 numbers. That's how fast these arrays are. Okay. Now you just find h. Exactly same thing. I'm not doing anything else. In fact, I copy pasted this program. It's the same program. Upar aur niche. I just have changed the variables from day to day array and delta to delta array. Nothing else. And there you go. Doing the same calculation again, it calculated, done. Now you have an array T which contains the time of every day, time of every day of the year, and then you have an array dr which is the day of the year, right? And now you might want to display the data, you might want to visualize the data. In Python, there comes a program called matplotlib, a library called matplotlib. It has a subprogram called pyplot, and I give it a nickname called PLT. It's a standard convention. And the trick is just write PLT. PLT is a program which has a subprogram called plot. PLT.plot, you call that plot program. Ask it to make a graph of day array versus T. You can just give a grid to your graph. You can give a X label, Y label, and press shift and enter. And there you go. This is the graph. So it's simple. You have day of the year and you have day length. So you see somewhere in June, which is mid-year, 6th month, 180th day, the day length is maximum. And this is, by the way, done for the location of red fault. If you change the location, things will change and the day length will be different. Okay. So this is somewhere around 14 hours here and somewhere around 10 hours in January and December. Okay, so it's pretty interesting. We solved a very interesting problem. One thing which I want to give a disclaimer on, that this formula won't work if you cross 66.5 degree parallel, that is in the Arctic polar regions, both in the North Pole and South Pole. You must have heard that sometimes there is sun for all the 24 hours and sometimes there is sun for less than 24 hours. So there you just have to make some modifications. Okay, you have to put a upper limit that the sun will be above the horizon for all 24 hours. So yeah, that I'll just not go there. Okay, it will take more time. Instead, I thought that we should solve even more interesting problem. So what we solved is, what is the time for which the sun is above the horizon. But a more interesting problem would be, what time is it? I am just about to finish. Okay, it will just take 10 more minutes. So it was scheduled till 5:30, but we started a bit late. Okay, so so one of the problem is how long is the sun above the horizon? But a very interesting problem is what time the sun will rise, what time the sun will set, and even a more interesting problem is what time a star will rise and what time a star will set. Okay, these are solvable easily using Python. So what do? Here you import more programs from astropy.coordinates, skyquad, earth location, alt as getSun. GetSun is pretty interesting, we'll talk about it. Look at this slash over here. This I have knowingly put here. So what happens is sometimes your lines are too long. In Python, in Jupyter Notebook, there is no restriction on how long your line can be. Okay, like you can literally type everything. You can just keep on typing here. You can even cross this barrier. The cell will become longer. It's allowed, but it just looks ugly. Okay, so sometimes if you want your code to look a bit better, you just have to add that slash and start writing in the next line. It's always allowed. Okay. So these are the functions I imported again. My observatory, it's the same. I didn't change it. It's the same line, red fort. And my phi is again the same variable. I just run it. And then there's a program, astropy.time. And in that, there is a subprogram called time. Somebody asked a doubt. Huh? No, I just. For constellations, what do you mean? So constellation is an extended source. It does not rise at a time. So, for example, a constellation rises slowly, right? First, a bit of constellation will rise, then some part of it will rise. Okay, so you can't say that a constellation rose at that time. You can say it for a star. But yeah, calculations are valid. Yep, it's. I am sorry, I couldn't hear. Hi Mukul, please meanwhile type your doubt in the chat, okay? Okay, now there is a library called Time which does the exact same thing as its name. It literally works with I guess Sujay he can't hear us, so I just muted Mukul. Could you just write in the chat that you should write in the text? Okay. I guess he can't hear us either. Okay. Yeah. So we know. Okay. What time this IST time module of AstroPy works in? It obviously it works in actually something called as UTC. Okay, but it's similar to the GMT. Europeans ruled the world, made everything theirs, so the zero of the time passes through their places. And there you go. You have to convert it into Indian Standard Time. So, Indian Standard Time, as we all know, is 5.5 hours ahead of GMT, or to be more precise, this is UTC. Okay. By the way, some interesting fact I just got to know. We were taught that this Indian Standard Time ke liye, the longitude, it passes through Allahabad, but I just last week, I guess, I was watching Mirzapur, and that's when I knew that it passes through Mirzapur. It's near Allahabad. So it's an interesting fact. Do we have a doubt? You can. Yeah, any object. I did not make a description distinction. It can be anything. Okay. Okay, right. So I just give my computer the date of today. This is exactly today. Today and noon. So the calculations, because noon is usually the reference. So I just give the time of noon IST, and I just give the date and time in this very specific format to this program time, and then I just subtract IST difference because I want to work in India and we are 5.5 hours ahead, so I just go back, right? And there you go. So this gives a time. So this noon IST is a time object and it contains the UTC of this particular date and time, and subtracted from that is the IST, the time difference. Okay. Now, what I make is, I make an array of 24 hours, but R is a big step size for any calculation. So I make a step size of 5 minutes. So I divide 24 hours into a grid of 5 minutes. and then I do the further calculations. I give it units, very important, very beautiful also. In AstroPy, you can give units to your data. So I tell my computer, okay, I create an array, but this array, it contains time, and time is in minutes. Okay. You could take a smaller step size. It's always allowed. You can work in 8640000 seconds if you wish to. Right. And then I make an array time which starts from noon IST and then goes to the next noon in intervals of 5 minutes. Okay, so really I'm just creating a data set for each 5 minute of a day where I want to find the location of any object on the sky. So I just run this command. There you go. Now this is important. I had a local coordinate system. I had an universal coordinate system, which is the celestial sphere. The local coordinate system was the horizontal coordinate system. I did not talk about how to connect them. So you have to connect them, of course, right? The Python, it has a very easy function called alt-as, which just connects your, which just creates local frames, okay? We just create a frame object, something called as a frame object. It's just a frame, okay? It creates a frame for every time, for every location you enter into it. So I was making a code for Red Fort Delhi, so I give it a location of Red Fort. I give it time. What was time? Time was this. Today's date minus IST difference plus an array which means basically this time over here is an array of a day sampled in 5 minutes each. Okay. So I have just put a type here. Okay, whenever you are confused on what really an object in Python is, just type this command. type parenthesis frame set, which is the object here. So these are alt-as frames. And Python does it automatically. You had to do nothing and it did it very fast. This frame set, it has information, it has tremendous amount of information about the horizontal coordinate system at a location at every time of the day, which is very, very fast and elegant and beautiful. And now I do it again. So skycode, I call skycode, I ask it, I give it a name Vega, and there you go. It just returns the Vega key coordinates, and this is beauty. I make an object called Vega Delhi, which is the coordinates of Vega with reference to the local coordinate system in Delhi, and the command is simply transform to. That is it, as simple as that. You had array deck of an object, you just write transform to the frame set, which was a set of frames of sampled at 5 minutes for a location, and that is it. This transform to does the job. In principle, it can be done with math. It will be tremendous amount of trigonometry, of course. Before computers, also people did it, but AstroPy does it very handy. And look how fast it compiles. Look at the black dot, just black dot over here. And just press shift enter, and there you go. It converted. So I had now what do you have? Vega Delhi. Let me just type Vega Delhi, just a variable name. So it's a skycode object which basically took in the array deck of Vega and took in the location of a place as well as the time samples of that location for a particular date, and it made an object Vega Delhi which contains information about altitude and azimuth of Vega in the city Delhi, or precisely over Red Fort. And to quickly just let's remind ourselves of what alt-as were. Alt-as were the coordinates in the horizontal coordinate system, right? So what the problem we are concerned about is altitude really right now, okay? So we want to find what are the times when altitude of an object is greater than 0, that is, when is it above the horizon? And we have that information. Now how to interpret it? Plot it. So I had time array, I converted into hours. I had Vega Delhi array, I took in the alt object. It's an object, I took in the alt attribute of it. I just used the same command plt.plot. I gave X label, Y label, I gave its yeah. I gave, okay, let me just first make a plot and then tell you what these lines say. Right. There you go. This is the plot. Now I usually like my plots to have grids, and I want to just modify my text. So these texts don't look really nice to me. These are 0, 5, 10, 15, 20, 25. I'm studying something for 24 hours. So I would really like my text to go from 1 to 24, and that's 0 to 24. That's why np.a range 13. Now that's what they'll do. I want my y limits from 0 to 90, and I want my x limits from 0 to 24. I don't really want to see 25 over here. Right? Why would I want? And then I don't even want to see these negative altitudes, because these are the times when the object will be below the horizon. And I'm done the code. Now I usually like it with grid, so I just write plt.grid and run. There you go. So this plot, this is the solution. This plot, it tells you time from noon. Remember, we started with 12:00:00 because that's the standard convention. So these hours are counted from afternoon, not from midnight. Okay, it's an opposite convention. But it's easy to see. 4 really means 4. It just means 4 p.m. and 16 means 4 a.m. Okay. So you see that in Delhi at Red Fort, Vega, it will rise somewhere around 4 a.m., 4 p.m. and it will set somewhere around 7? Yeah, 7 a.m. It's beautiful. We did nothing. We just type a few commands. This code, it's hardly a 25 lines code, and it solved a very interesting problem. And okay, this is one thing. So basically, you might want to know that what time you can see it. So for example, it will come out at 4 p.m. That is, it is already out. Vega is already in the sky, but you can't see it. For clouds, of course, but because sun is also overhead, right? Sun is also above the horizon. So you might want to know when the sun will go down, right? So the times when you can see Vega will be when sun is below the horizon, and you can exactly do the same thing, right? So for sun, you don't really need to go to sky chord. Sun is a special object. There is an object called get sun. You just enter time, and remember this time is an array. So this will return sun, the sun object for a complete day sampled at 5 minutes. Okay. So this gets sun at every time, and then you transform to sun Delhi using the same command. You run it, and now you make a plot combining sun and the Vega. Right. So you can make different plots on the same graph. So these are two plt.plot commands. One is for sun, one is for Vega. I give them labels, Vega and sun. I give them markers. I say that okay, Vega wala curve should be blue and it should be a normal curve. I say ki sun wala curve should be a dashed curve, and K for black. Okay, I don't know where that comes from. And then I write a command plt.legend. This legend prints these labels. Okay. And then usually I give grid, I give X label, the label on X axis, the label on Y axis, Y limit, X text, X limits, and title. Mega observing time at Red Fort, Delhi. And I press Shift Enter. This is it. So you see that the sun in Delhi will set at around 7 p.m. It's slightly more than 7 p.m. Of course, you can check. You can just ask Python to go through the array and check exactly when the altitude becomes less than 0. That is when the sun will set, and the sun will rise tomorrow just before 6 a.m. Okay, and in between you can observe Vega. That is somewhere from, let's say, 8 p.m. to somewhere around 5 a.m. right? And you can see what altitude you will see it at. Okay, and you can also print the azimuth of Vega to see where exactly you have to look. Right, you need to know the azimuth as well. Where exactly do you have to look, east, west, north, south? You can make a plot of that. Okay, so this is it. You can in Python you can save figures. So to save figures, you either okay, okay, this is not interactive. You can just write PLT. In other compilers like Spider and even ID, I guess you can save figures directly. But here you can write a command as well, plt.savefig. Let's just name it fig1. I can save it as a PDF. I can save it as a, by default, it's a PNG file, I guess. I just shift run it. And there must be a figure out in the library. Yeah, there you go. This is done. This is stored. Right? You can store it as a resolution. It's very handy. You can do anything you wish to. This is all. Any final? Okay, let me just. So it goes the other way around, right? If you have, so how do you do kinematics? It's simple, right? You ought to have velocity first and then you can tell motion, right? So it's the opposite way around. I mean, RA and deck are given, but if you're talking about, so stars actually move, they move with very slow, not really very slow velocities, but very slow angular velocities. That is, from Earth's perspective, they are very far, so we see them moving very slowly. Okay, but yeah, it's the opposite way around, obviously, right? We first somehow know the velocity of the object using some specialized method, and then we tell that okay, the object 100 years ago was at this array deck, now it will be at this array deck. Okay? Hmm. Oh, that's interesting. There must be I mean, one thing is you can just go to the various archives, there will be times there. But if you are asking that question with respect to Python, I don't really know if there is some inbuilt library. There might be, but yeah, the another way is to just Google up archives, all the telescopes report and store the information all over the internet. Hmm. Any other questions? Most welcome. All right. Hmm. Right. Okay.